Well, thank you very much, Trigger, for introduction. And my thanks to the organizers for including me in this DFT fest, if I could put it that way. What I want to try and do is to just give a historical overview of some of the places where we've been involved in various aspects of DFT over the years. You'll see some of the same events that Evert Jan referred to and a few different ones. The sort of perspective that I want to build is this multi-scale modeling. It's something that we've been worried about for many years, if you like. What I would like to do is be able to describe chemical reactions in complex environments. So if you take that as a driving force, then what we're going to do is, first of all, what I call a retrospective and fast forward, and it really will be fast forward. I think in particular for this audience, we don't need to dwell on many of the details. And I'll try to bring it up to date at the end with some recent work we've been doing using machine learning to help us speed up calculations, and even quantum machine learning. So we're starting to worry about quantum computers and how they might eventually affect our lives. So here we go. Button down your collars. The 1920s, well, we had this fellow, Schrödinger, with the wave function, and you all know that anything you're allowed to know about a system is contained in this many electron wave function. Weak correlation, strong correlation, entanglement, all of the things. If you take the time-dependent version, you can include coherence and decoherence. So that's sort of the starting point. DFT, in some sense, is just a way to get approximate solutions in a very clever way. The first density functional, we heard the words Thomas Fermi mentioned a moment ago. It's the kinetic energy, which, as Evert Jan indicated, is of no use for chemistry, so to speak. But it certainly is, I think, the first bona fide density functional that I'm aware of, at least. Coming to the 30s, this man brought exchange into the world with the homogeneous electron gas exchange treatment, this functional that has rho to the 1/3, rho to the 4/3 if you multiply it by the density and integrate over all of space. Jumping to the 50s, the 40s, the world was occupied with man's inhumanity to man, and we hope we never get there again. But after the war, things picked up in a number of labs, and 1951 was a banner year, I think, for the likes of us. Both the Rotan-Hall method of self-consistent field approach to the many electron problem was introduced. And John Slater wrote this 1951 paper that Evert Jan mentioned, which I think is one of the hallmarks. It's certainly the first time that we see this rho to the 1/3 in terms of electron-electron interactions coming into real calculations, I would say, with this parameter alpha in front of it in order to be able to link to experimental values in some sense. So this was the idea of a pair correlation function, a hole, if you like, the exchange hole, or the exchange correlation hole, which, if you like Einstein's idea of Gedanken experiments, imagine you're riding on an electron, this one, let's say, and you see around you some potential contribution to the potential, which is keeping electrons of the same spin away from you, which is basically the idea of exchange. And all of this was laid out very, very nicely in one of my favorite papers, actually. Just this slide and a few others come from a graduate course I gave a few years ago, in which the sort of birth of the local density approximation is described not only in equations in this paper, but in terms of words. Slater was a master of scientific writing. If you worked with his books or just reading the abstract, which I won't take time because I don't have time to read it with you, but you can actually see the process of going through this, imagining an exchange cloud, which is around each electron. It's averaged over all of the orbitals that are occupied. And then in order to do some useful calculations, you bring in a homogeneous electron gas model, and there you have the LDA. So perfect word picture as well as an equation picture that comes out of it. Into the 60s now, where these gentlemen you're all aware of, Cohn and Sham, 64 and 65. I think I don't have to dwell too much on those equations for this audience. Coming into the 70s, we're finally getting to my world. I was, let's say, coming of age in some sense. I was a postdoc at the General Electric Labs in the 1970s with Dick Mesmer. This sort of goes in parallel to Everett Jan's comments about there being a great interest and a thirst for anything in industry which could give you information on the electronic structure of complex systems. In our case, these were little transition metal clusters which we were trying to use to model catalysis. And this was done with the X-alpha scattered wave method. Sometimes the scattered wave part of it is lost in the discussion, but I think it has a fair amount to do with two things. First, with giving enough efficiency so that you could solve fairly complex systems. And second of all, with causing inaccuracies, which got a lot of ab initio quantum chemists disturbed. We mentioned the water molecule, which if you try to optimize it within this X-alpha scattered wave method, turns out to be linear, which most chemists won't like very much. So there's lots of stories could be told about Keith Johnson and John Slater and the way they popularized the X-alpha scattered wave method. Oversold is a word that has been used, and perhaps rightly so. This was a time. I also had Karl-Heinz Schwarz, who basically got us the values of alpha for the periodic table, and this was an achievement which helped people to know how to get calculations started. So what is this muffin tin? Well, it's a tin that makes muffins. And if you think of spherically symmetrical potentials and constant regions in between them, it looks like a muffin tin shape from the outside. It gave interesting orbitals such as this for, I forget even which molecule this is, maybe it's silicon-2 or something, but the scattered wave approach guaranteed continuity of the wave functions at the boundaries between the spherical regions and the constant potential regions, but it didn't ensure the second derivative, the derivative of the functions, the first derivative. So what you see are these sort of unsightly kinks in the wave functions, which a typical Gaussian user would just be aghast that this ugliness could be taken as serious science. They just look ugly. So in terms of a Kipling-esque, make allowance for their doubting too, you can perhaps see that this wasn't so welcome in the realm of people who are trying to do high accuracy ab initio quantum chemistry. Nevertheless, we could find geometries even, despite the linear water paradox, but in an indirect fashion. So this is an example where we looked at some aluminum 22 atom clusters, which I think certainly at that time you wouldn't want to try to do a correlated ab initio calculation on a system of this size. We could do it quite readily, put an oxygen atom down on it in various places, and then compare with experiment with some UPS to try and determine the position of the oxygen atom as in an indirect fashion by varying the position and looking at experimental properties, the density of states, essentially. Then coming into the 80s, well, I moved to Montreal, and this is the demon part of it. Demon means density of Montreal, if you like that. I sometimes say that this is what they did to celebrate the fact that the library building at the University of Montreal. If you ever wondered about the strange capitalization, it's lowercase d, lowercase e, capital M, lowercase o, lowercase n. And that sort of looks like the shape of this main library building at the University of Montreal. So while my students and postdocs were working hard on the contents of Demon, I came up with this, with this title. Very, very proud of it. This is again from a grad course I gave some years ago, with apologies to any friends who aren't on the list of people who I was thinking of at that particular point in time. Those who were developing density functionals, including Axel Beck and John Perdue, and some of their predecessors and their successors who were active more or less in this time frame of the 80s or so, working on exchange correlation holes and trying to improve the accuracy of density functionals. I also put Michele Paranello on this slide, just in terms of complex systems, eventually multi-scale modeling, as being the other side of my world, in which we want to be able to move atoms around, do dynamics, look at thermodynamics and sampling and things like that. And probably Michele is the master builder in terms of bringing ab initio molecular dynamics into being. You know, whether it's Carr-Paranello dynamics or Born-Oppenheimer molecular dynamics, the idea that you don't have to use a force field to do dynamics. In fact, during this time frame, I think it was almost like there were two solitudes. The molecular dynamics chemists, at least, would have their meetings and talk to each other, and the quantum chemists would have their meetings, and never the twain would meet. Well, I think people like Michele did a lot to bring those two communities together. Okay, in our particular case, Jan Anselm came from Shigeru Utsunaga's group, and he basically brought Gaussians into our world. We worked for a while with Brett Dunlap's program after I went to Montreal, but we decided to make our own program. René Fournier and Jan Anselm worked out the gradients. Going into the 90s, just barely into the 90s, was the first paper on what we now call Demon, which Alain Saint-Amand wrote. Alain has a remarkable brain. He would sit down at his computer terminal and program the Obaraseka two electron integrals directly from the journal, which impressed the heck out of me. And then that brought us to what we now call Demon 2K, which is density functional theory. We put a lot of emphasis on fitting. In fact, we call this now auxiliary density functional theory because it's a complete theory which uses the fitted density everywhere, including for the exchange correlation parts. That gives great speed. We use Gaussians, and this is sort of an upside down Jacob's ladder of the various exchange correlation functionals that can be used. Moving along, I had quite a big group in the 90s. Fiona Sim was there, Imre Papai. If you wanted to get into biological things, well, you have to worry about hydrogen bonds. The first thing to realize is that the LDA is completely inadequate. You make errors in the binding energy of the water dimer, which are equal to the bonding energy itself. But the generalized gradient approximation, in this case it's Becker-Perdue, gave an error in the bond length of about 1/10 of an angstrom and a binding energy of about 1/2 kilocalorie per mole, which are not highly precise numbers, but they were at least enough so that if you kept your wits about you, you could get into the bio world of hydrogen bonds and the like. Sometimes tell people that in biology you can die for 1/2 kilocalorie per mole, which we should keep in mind. But nonetheless, you can go ahead and do good science with this. Dongqing Wei did the first QMMM calculations using Demon 2K, I should say. This is an SPC water molecule interacting with a quantum mechanical water molecule. What else did we do? A lot of work on transition metal clusters. This is a nice one for niobium-3 and its ion, niobium-3O, because it's a good example of, again, using indirect methods in order to determine geometries. I would say this, in this case, a categorical determination of the structure of this niobium-3O cluster. Basically, if you do all of this and compare with photoelectron spectroscopy, you find that the planar form matches and the 3D form just simply doesn't. So we know now that this cluster, this particular cluster, is of the planar form. And also your 1990s were the Nobel Prize. 1998 for Walter Cohn for DFT, along with John Popel for ab initio quantum chemistry. Coming into this century, I moved to Calgary. I think you can see some of the attraction of Calgary. This is part of the pre-candidacy exam in Calgary. If the PhD candidate doesn't stay on the bull for 8 seconds, that's it, no PhD, no matter what. Dispersion, as we all know, is important, and we also contributed something to the history of bringing empirical dispersion corrections into DFT. I see Stefan Grimme is in the audience, and he also made great contributions. This was with Pavel Hops and Peter Jureska, who was a postdoc with me for a couple of years. Dispersion is important. We did are doing a lot of Born-Oppenheimer molecular dynamics work on systems like these lipid molecules, which have 100 atoms or so in them. And our thesis here is that you can see enough complexity in the molecule itself that there's something like a melting transition, even before you deal with long-range intermolecular interactions and the like. To the tens, well, this is basically the era of QMMM, multi-scale modeling. The late Sergei Noskov, for example, we figured out how to get charm and demon together so that we could do calculations on systems embedded into a molecular mechanical potential and look at more realistic systems. A fair amount of work on electron tunneling using David Barreton's pathway approach. This is one of my favorite diagrams that Aurélien Delalande made, because I think it captures the spirit of multi-scale modeling. Let's just spend a minute or two with it. If the actual calculations that we did had to do with the transfer of an electron between two proteins in this respiratory chain. We want to get an electron from a protein called MADH to another one called amethionine. So that's an electron transfer event. And it's part of many electron and proton transfer events that eventually lead to this ATP synthase protein, which makes ATP from ADP. So this is the energy source in your cells. If you want to understand this, you can use the usual reductionist framework, go down in scale to eventually this level where we did actual molecular dynamics calculations. And you can see there are the two proteins, and there's some water molecules in between, which turn out to play a major role in terms of the electron transfer. Going further down, we see the Marcus theory of electron transfer. These two intersecting parabolas and the diabatic scene, non-adiabatic coupling constants come in, and that's something that can be calculated. And there are even treatments down dealing with the nuclear wave packets that come in terms of nuclear and electronic coherences that can influence the rate of transfer. So all of those have to come together. And if you want to deal with macroscopic or at least microscopic, micron scale things, cells are micro, proteins are nano, then you have to be able to integrate up this side. And eventually, if you could do this for all of the various biochemical processes and get the rates for them, then you could put this into a kinetic Monte Carlo or some other microkinetic model and actually have, as a result of this whole coupled calculation, the rate of production of ATP, which could then go into someone else's model for even a higher scale. So that's the kind of philosophy, if you like. No one has done this yet for a system as complex as the respiratory chain, but I think with additional computing power, it's certainly imaginable. We've done 2 or 3 reactions. You'll probably have to do 2,000 or 3,000 reactions to get to the level of complexity that we would like to. This was the next sort of computational chemistry Nobel Prize in 2013. It was a 15-year interval between them for Karpus, Levitt, and Borschel for multi-scale modeling, for QMMM, if you like. And this is actually one of my older slides. I remember carrying this one around in an armful of transparencies for overhead projectors. And so it's been around for 30 years or so, where if you want to look at some complex system, you have to break it up. And the poor students these days, if you want to deal in this kind of complex chemistry, you have to learn some quantum chemistry. You also have to know dynamics and statistical mechanics, and even perhaps some more engineering, computational fluid dynamics, or kinetic Monte Carlo schemes. One example, which comes from the world I live in, the Alberta oil sands, which are shown here. And the good news is there's a lot of energy in these. The bad news is there are environmental impacts. And some of our friends are trying to improve the upgrading process so that this can be done in a more reasonable way. Which brings me to one example of QMMM. This, in fact, is not real DFT. It's DFTB for the quantum part of this QMMM approach that Xingchen Yu performed. Basically, he's trying to hydrogenate a benzene molecule. You can see a hydrogen atom coming in here, attaching to a carbon on a benzene. And it's being done on a molybdenum carbide nanoparticle with about 100 atoms or so. This is still one of my favorite movies, just because I found it so surprising that there was such a lot of movement in the molybdenum carbide nanoparticle. I naively, coming from a background of surface chemistry, I thought molybdenum carbide is hard and it's not going to move very much. But that's certainly not the case at 400 Celsius. And the entropic part of the free energy diagrams are hugely important for this kind of system. Indeed, it even looks like general ideas like a particular reactive site. Xingchen put this down on top of a 3-fold site on the surface, but you can see it doesn't really want to stay there. When meanders over onto a 2-fold site, etc. So even some of these classic ideas for how to look at surface reactions might be worthy of a different perspective. And that sort of theme is being taken up by a lot of people in the heterogeneous catalysis world right now. So that's my second favorite movie of all time. Coming now into the 20s, I have a feeling I'm rushing. No, I'm okay. Yeah. We'll have some time for discussion. I want to get into what I've called the robots, and that basically means bringing machine learning somehow into our world, symbolized on this slide by a program called MLChem4D, which our colleague Maicon Lorenzo has written. These are Python scripts which sort of match machine learning with materials data and either experiments or computation. The idea here is that we would love to be able to do more and more complex systems with finite computing time. And if machine learning can help us to save computing time, then I'm all for it. Well, this movie actually was what prompted me to get into the machine learning world, just because even though this was a fine paper that Xing did, editor's pick and all of that sort of stuff, in order to do these umbrella sampling calculations, you have to choose a reaction coordinate. So Xing just chose a CH bond distance as a natural one, but I think we'd probably all agree that the true reaction coordinate is more complex than that. So that got me to just reading about a number of ways of looking for reaction coordinates or collective variables and using machine learning to help in that endeavor. Got a book maybe 5 or 6 years ago, a couple of books, and started to read it. Surrounded myself, as usual, with energetic younger people. And in some sense, at this point, we've now written some machine learning platforms with titles like QML Material or MLChem4D, etc., which implement machine learning algorithms. And we're sort of pairing them with Daemon 2K or other electronic structure codes. Just one example comes from Lisandra Barrios's PhD work, which is looking at nickel-Syria catalysts. So these are still a great challenge if you want to do anything ab initio with them. The sort of triangle of the workflow in this is you start with a structure generator. I should say that we have learned over the last few years that something called active learning is a very powerful machine learning paradigm, which works with a remarkably small amount of data. So for example, we would start off with maybe 15, 20 randomly generated structures. That's the structure generator part of this. Then we'd do DFT or maybe DFTB calculations on those structures. Then we'd give it to the machine to predict the next ones to look at. And if you do this for a few iterations, it actually converges quite nicely. That's the actual workflow. A genetic algorithm is thrown into the middle of this just to generate more diversity in terms of the structures that we've been looking at. So this converges quite nicely in a few new calculations or a few local optimizations. You converge to the global minimum structure, which is at least a goal along the way to dealing with catalysis. Just to show you that the active learning part is right, this is a nice little experiment that Lisandra did. She had a distribution sort of at the end of the calculation, which looked like this, and she removed all of the low-lying structures and then started the process again. Within just 2 iterations, she's already populating the lower-lying structure, and within about, I think, 22 cycles of active learning, she's found the full distribution. So the active learning aspect of it is really working as it should. You can see this a little bit in more detail. At the start of this process, if you have the first 100 structures and you look at the training set, you'll see it's fitting this training set very well, whereas on the testing set, it's doing rather poorly. That's the signature of overfitting in these machine learning. You're hitting all of the points, but nothing in between. Well, as the active learning process goes on, these then come out to be fairly equal to each other, so it's working well. The last few minutes I'll spend on what I sometimes call quantum chemistry. I live with quantum information people in IQUIST, for example, people who are highly concerned about entanglement and some of these basic superposition properties of quantum mechanics. So anything that you do with normal quantum chemistry or particular with mean field approaches like DFT, it's just not worthy of the title quantum in this context. I sometimes call it quantum chemistry, that the remaining part of the talk will involve quantum computers and trying to see whether they can help us along the way or not. The first example, about a year ago, Moseyev and Sergey did a quantum machine learning exercise. This is all done, I should say, at the outset on simulators, something called Qiskit that IBM has, which emulates quantum computers. So we haven't yet put them on a real noisy machine yet. But to make a long story, a longer story, a little bit shorter, this is a case study on AV03 perovskites. So we have a few hundred AV03 structures. Some are perovskites, some are not. And the machine's task is to classify them into these two classes. We had some literature studies on this problem using classical machine learning techniques. This particular one is a random forest. And if you look at the overall accuracy of the test set, sorry, the training set, it's 0.97. The test set, it's 0.82. So just a good fit, but it's indicative of some overfitting. When all of the dust has settled, we put this into a quantum, parameterized quantum circuit. This is essentially the equivalent in machine learning of Alan Asbrook-Guzik's variational quantum eigensolver, except instead of minimizing an energy, minimizing a Hamiltonian, which is parameterized, we're minimizing a cost function, an error function in the machine learning. And it has these various quantum circuits, which we can go into if anyone is interested. But the bottom line here is that by entangling 5 features, the test accuracy and the training accuracy are essentially equal to each other. So somehow entangling these features is improving the overfitting that was there in the classical output. More recently, this work is still under review at Scientific Reports. It's on the archive if you want to read it. It involves basically just using quantum kernels in Qiskit or another platform called SQU Learn, and it's been integrated into these software, these Python packages that Micron has done. So here we use, let's say, a classical, these are hybrid approaches. You use classical computer to optimize parameters, but the actual quantum kernel and either support vector or Gaussian processes are done with quantum feature maps and quantum kernels. This is just one example. It has to do with looking at a data set of some 74 perovskites with the piezoelectric coefficient as the target. This black line is the classical support vector regime, support vector regression using the expected improvement acquisition function. The colored lines are various variants of quantum versions of this same support vector regression. And you can see that there's a clear improvement in terms of the rapidity with which this system converges into the expected maximum value. Now, we've done this for various other properties, and the bottom line is sometimes there's an improvement, sometimes there isn't. We don't know in detail why that is. The best sort of attempt that I've come up with so far would be that the quantum improvement might be there if you have somehow rough, non-normally distributed data sets. If you have a normal distribution, a smooth distribution, then the classical algorithms already have everything they need. They're on their home turf, so to speak. But if you get into some other kinds of distributions, then maybe there's some advantage to bringing in quantum aspects to the machine learning. This is at least similar to a conclusion from Christoph Simon, our co-worker in the physics department at Calgary, who did some time series, and there he found that high frequency yields an advantage in the quantum world, whereas low frequency doesn't. So maybe you could imagine that some future time, this might be part of a pre-screening protocol for when do you use expensive quantum computers, when don't you, and all this kind of things. It's hyper early in this field, certainly for us, but I think in general, people are just trying to get their bearings on when you might find any quantum improvement, let alone the so-called quantum advantage, which is a loaded kind of term. So that brings me fairly much to the close of what I wanted to say. This is just to integrate again that certainly I think DFT for the foreseeable future will be there in this sort of multi-scale modeling world in a big way. I believe that machine learning definitely will help us to accelerate. I think we have enough experience as a community to know that there's a role for machine learning. I'd still put a question mark on whether the quantum computing aspects will feed us or not. Shout out to the sponsors, and also I'd like to give a shout out to some of my favorite people, the Daemon developers. We meet almost every year. This time it was on Zoom. A couple of years ago it was in person. Actually, we were in Stockholm last June with Lars Peterson put together the meeting, but I couldn't find a picture from that meeting. So with that, I'll be happy to try and answer some questions.
Thank you very much for covering all the 100 years, so to speak. So, questions, comments from the audience?
I have spent a lot of my career worrying about chemistry students knowing too little quantum mechanics and living in a world totally dominated by it. So when I hear your story, you wonder what the future will look like. Will it be possible for chemistry students to rely on artificial intelligence devices that already know quantum mechanics, and that you can ask to provide you with answers in such a way that the problem of really not understanding quantum mechanics doesn't cause trouble?
Yeah, I think for my own opinion, for the general chemistry population or physics population, for that matter, people who need to do calculations to get some idea of properties of a particular system, the kids these days are already living in that world of things on their cell phones, which they can work with, even though they don't know everything that's under the hood. So if you don't need to know everything that's under the hood, then you definitely should take advantage of every aspect of artificial intelligence that you can. Now that implies, of course, that you need specialists who do know what's under the hood and can interpret what's going on, and that would be the work of audiences such as this. I'd be optimistic that we'll get to some reasonable this.
I just wanted to make a little historical remark to young Dennis here. I think Dirac, in a 1931 paper, writes down the exchange energy of the uniform gas when he's creating time-dependent Hartree-Fock. He sort of does that in order to get that. But Felix Bloch wrote it down first, as far as I know, in 1929, even though I think lots of people sort of refer to Dirac for that exchange energy, but it was actually Bloch who first wrote it down.
Just corrected.
This is true. Bloch's paper was his PhD thesis in published in 1929, calculation done in 28, but he even did it for a spin polarized electron gas, and then I'm very pleased to hear that, because most people don't either read the paper of Bloch or recognize what fantastic work is in there.
Well, I didn't actually read it because it's in German, but, I could read the formulas. Right?
That's good.
Okay, we have time for one more. Yes?
So I wanted to ask Dennis because like he had this nice paper in chemistry through the periodic table in ACS like 1889, I think. And yeah, so I just wanted to point out that I read it like recently, and it has stood the test of time. So I think it was a really nice article. So
Okay.
what do you think?
So everyone should go home and read that paper.
So if you know, like you have like 1 minute, so what do you think has been the biggest improvement since those days when you wrote that?
I think better and better functionals, which are sort of homing in on being able to incorporate things that previous versions were failures. I sometimes talk about beautiful failures as you go along. So, you know, if we can get to really doing strong correlation with something like a density functional that doesn't break the bank in terms of its own complexity, then that will be great. But I'm not sure. I don't have a solid crystal ball, particularly if there's some real advantage on quantum computers for one method or the other. I think I'd probably bet on wave function methods if I had to at this point. Then maybe we don't have to worry about a density functional. We can just put it on the quantum computer and get the many electron wave function, which would be fine.
Okay, thank you again, and thank you to both speakers.